Good day everyone. This is the last group's presentation, and in this video, we are going to discuss solution to ordinary differential equations, which will be centered around boundary value problems. I am Anthony Talsik, and I'm your first presenter. A differential equation is an equation with a function and one or more of its derivatives. This equation have wide application in various engineering and science disciplines. In general, modeling of the variation of a physical quantity such as temperature, pressure, displacement, velocity, stress, strain, current, voltage, or concentration of a pollutant, which the change of time or location, or both, would result in differential equations. In fact, many engineering subjects such as mechanical vibration or structural dynamics, heat transfer, or theory of electric circuits are founded on the theory of differential equations. It is practically important for engineers to be able to model physical problems using mathematical equations and then solve these equations so that the behavior of the system concerned can be studied. By extension, differential equation can either be partial or ordinary. A partial differential equation, or PDE, is an equation that depends on one or more partial derivatives of function of several variables. We will not be looking into partial differential equations much further because our focus is on ordinary differential equations. So now, let us define an ordinary differential equation. In mathematics, an ordinary differential equation, or ODE, is a differential equation containing one or more functions of one independent variable and the derivative of those functions. The term ordinary is used in contrast with the term partial differential equation, which may be with respect to more than one independent variable. In numerical analysis, ordinary differential equations can be solved using various methods, some of which are through problems were already discussed by the preceding group, and in continuation to this.
Good day, everyone. We are with Group 4, and as you can see, we will be tackling the solution of ordinary differential equations about boundary value problems. So, but before that, let me introduce myself first. I am your reporter, Ms. Ria May Ubas, and I will be tackling or explaining to you about the boundary value problems and its general approaches. But before that, let me differentiate first the initial value problem and the boundary value problems. So first, what is initial value problem? So initial value problem, even if no one will say, no one will tell to you about the meaning of it, but I guess everyone or anyone can automatically identify what is the initial value problem, or from the word itself, initial. So initial. So initial value problem does not require to specify the value at boundaries. Instead, it needs the value during initial condition. So in vernacular terms, initial means sinugdanan or before. So before or after, muna si before. Okay, so this usually apply for dynamic system that is changing over time, as in physics. So to give you an example, initial value problem may apply in solving a particle position under differential equation, where as we need the initial position and also the initial velocity. So as you can remember our physics, so in determining such equation or such solution or problem, there is that one topic that we should identify the initial position and the initial velocity. So without these initial values, we cannot determine the final position from the equation. So I guess it's a little bit highlight for the topic. So I hope you can identify or you can understand what I am going to talk about. So initial value problem compared by it is the boundary value problem. So in contrast, boundary value problems not necessarily used for dynamic system. So instead, di ba ganiha, initial value problems can usually apply to dynamic system in which it is changing, di ba? So na initial doesn't change. So dapat pangitaon na yung initial. But there is a boundary value problem. So boundary value problems not necessarily used for dynamic system. Instead, it is very useful for a system that has space boundary. So to give you an example would be shape from shading problem in computer vision. So to determine surface gradient from the PDE, so one should impose boundary values on the region of interest. So it's a little bit introduction for it. So we will be giving you some examples or ideas about it. Okay, so here we go. Boundary value problems. So a boundary value problem is a system of ordinary differential equations with solution and derivative values specified at more than one point. So most commonly, the solution and derivatives are specified at just 2 points, the boundaries, defining a 2-point boundary value problem. So I hope you can clearly view on the picture beside it, because it clearly tells us the difference between the initial conditions and the boundary conditions. So it is basically starting from the zero as usual, and it is telling us where could be the initial conditions and where could be the boundary conditions, or where could be the boundary conditions stop. So as you can see, I hope you can see it, the equation or the formula about the initial conditions were dy sub 1 over d sub t is equal to f sub 1, y sub 1, and y sub 2. The quantity of f sub 1, y sub 1, and y sub 2. So there's another equation, dy sub 2 over d sub dt is equal to f sub 2 times the quantity of t, y sub 1, and y sub 2, where at t is equal to 0, y sub 1 is equal to y sub 1, and y sub 2 is equal to y sub 2 as always. So in the initial conditions figure, you can see there are two lines that has been waving. Wave sila, no? So, dira ni mo makita kung asa ang initial condition, adto jud na siya padung sa iyang boundary condition, sa iyang last na condition. Like for example, y sub 1, where y sub 1 isag unsa ba na siya nga linya ang mubagis dira, as long as nisubay ka sa iyang process, nisubay ka sa iyang giagian, wala jud kay lain mapuntahan kundi ang tumoy ra jud sa iyang wave or sa line. Okay, isag asa pa na, bisag nagikis-ikis pa na sila dira, as long as kamao ka or kabalo ka sa process niya, asa siya niagi, at tulad ka mapadung sa iyang line, last point. So, for example is, walang siya medyo identical lang siya. So, identify rata nga ang y sub 1 is will end, of course, sa y sub 1. And the y sub 2 will eventually also end at the y sub 2. And then, as boundary conditions given the equation uh, d squared y over dx squared is equal to function of x and y. So we're at x is equal to 0 and y is equal to y sub 0 and x is equal to L and y is equal to y sub L. So based on the given example or the given figure, so boundary condition was only giving us one curve line or one wave line. So it's boundary to boundary. So kung asa siya nagsugod on in its x-axis and y-axis. So mustap po siya sa yung x-axis and y-axis kung asa siya like intersect. So for example, the first point of boundary condition starts at y sub 0. So eventually, mustap po siya right on the point na nag-intersect ang x and y axis. So sa nasa figure kay si L man, it is denoted as L. So we will be calling that as y sub L. Okay, so there are two general approaches of boundary value problems. So the first one is the shooting method, and the second one is the finite difference method. Okay, so actually, these two general approaches, I will be only giving you a highlight about this. So, shooting method versus the finite difference method. So, for the shooting and finite difference method, they are both numeric methods that approximate to the solution of a BVP or the boundary value problem to a given accuracy. So in this report, both methods were implemented in MATLAB and compared to each other on a BVP found in the context of light propagation in nonlinear dielectrics. So it was observed that the finite difference method is numerically more stable and converges faster than the shooting method. So to learn more or to understand more about this method, I will be giving you to our next reporter who will be dealing this and who will be explaining to you further. So thank you so much for listening.
Good day everyone, this is Nina Jennifer Vergara. In this part of the video, we will be understanding deeper what shooting method is. Shooting method. In numerical analysis, the shooting method is a method for solving a boundary value problem by reducing it to the system of an initial value problem. Roughly speaking, we shoot our trajectories in different directions until we find a trajectory that has a desired boundary value. So our first step in solving the problem is we'll demonstrate the shooting method with the second order ODE from the heater rod problem. Our ODE is second derivation of t plus h prime times t alpha minus t is equals to 0, which is from the derivation of Fourier's law, plugging Fourier's law into the heat balance equation and divided through by k. And our boundary conditions are T of 0 is equal to TA and TL is equal to TB. It expressed the second order equation into two first order ODEs. We let Z as the derivation of T and the derivation of z is equals to h prime times t minus t alpha. Substitute dz over dx is equals to 0.01 times t minus 20. To solve this equation, we require an initial values for z. For this method, we guess a value. Say z of 0 is equals to 10. Using a fourth order RK method with a step size of 2, a little bit recap, RK method is expressed in these equations. We obtain a value at the end of interval of t of 10 is equal to 168.3797, which differs and obviously lesser than expected value, which is that t of 10 is equal to 200. So make another guess. We say z of 0 is equal to 20 and perform again the computation. This time, we obtain t of 10 is equal to 285.8980, which is way greater than the expected values. So these are the values that we obtained. If then t of 10 is equal to 168.3797, and if z of 0 is equal to 20, then t of 10 is equal to 285.8980. And because the values are linearly related, as such, they can be used to compute the true value of z of 0 that yields t of 10 is equal to 200. A linear interpolation formula can be used for this purpose. We say z of 0 is equal to 10 plus 20 minus 10 over 285.8980 minus 168.3797 times 200 minus 168.797. Then we get the true value of z of 0, which is 12.6907. So let's understand more of the values that we obtain by using graph. So we can say that the first graph, it was the z of 0 is equal to 10, which is lesser than the expected value. And the second graph is z of 0 is equal to 20, which is much higher than the expected values. And lastly, z of 0 is equal to 12.6907, which shoots to the expected value. The next example is nonlinear two-point problem. Same as example number 1. A non-insulated uniform rod positioned between two bodies of constant but different temperature. Use the shooting method to solve for a 10-meter rod. ODE is second derivation of t plus h double prime times t alpha minus t to the fourth power is equals to 0. H prime is 5 times 10 to the power of negative 8 and t alpha is 20. Same process from example number 1, we express the second order equation into first two ODEs rather. We let z as derivation of t and the derivation of z is equals to h double prime times t minus t alpha to the fourth power. Then we use fourth order RK approach to solve this problem. The function integrated the equations based on an initial guess for z of 0 and returned the temperature at x equals to 10. The difference between this value and the goal of 200 was then placed in a spreadsheet cell. The Excel solver was then invoked to adjust the value of z of 0 until the difference was driven to 0. As might be expected, the linear case is curved more than the linear model. This is due to the power of fourth term in the heat transfer relationship. So, shooting method can become arduous for higher order equations where the necessity to assume two or more conditions make the approach somewhat more difficult. For this reason, alternative methods are available and it will be presented by the next reporter.
And finally, let us now proceed to our next and last method of solving ordinary differential equation, which is finite difference method. I am Joe Marama, the last presenter. In numerical analysis, Finite difference methods, or FDM, are a class of numerical techniques for solving differential equations by approximating derivatives with finite differences. It should be taken note of that this method utilizes approximation, meaning that there will be slight errors to its answers. Finite difference methods convert ordinary differential equations, or ODE, which may be nonlinear, into a system of linear equations that can be solved by matrix algebra techniques. And this is made possible by utilizing finite divided differences formulas. Let us first understand what finite divided differences are. Finite divided differences are substituted for the derivatives in the original equation. Thus, a linear differential equation is transformed into a set of simultaneous algebraic equations that can be solved using various methods. Finite divided differences can be expressed in three ways: forward finite divided difference, backward finite divided difference, and lastly, centered finite divided difference. The only difference between these three is on how they were derived using a graph of an equation. These formulas were approximated using Taylor expansion, meaning smaller increments or changes were incorporated to come up to its derivation. And since the formulas were only approximation, there will be small errors. I will now provide the finite divided difference formulas. The formulas correspond to their respective derivatives. The second layer of each equations in each derivatives is more accurate compared to the first one since more terms in the Taylor expansion were included. First, we take a look at the forward finite divided difference. Second, the backward finite divided difference. And lastly, centered finite divided difference. In solving, you are free to choose which of these three sets of formulas are you going to use. You can either choose forward, backward, or centered. However, centered finite divided difference is more recommended to use because it is more accurate compared the two. To understand this method better, let me provide an example. Given the boundary value problem, y is equal to 4 multiplied to quantity y minus x, where x is greater than or equal to 0 and less than or equal to 1, y of 0 is equal to 0, and y of 1 is equal to 2. Use the finite difference method to approximate the solution with h is equal to 1/4. What is the solution at x is equal to 0.5? Let us now start with the solution. First, since h is equal to 1/4, we divide the values of x from 0 to 1 into 4 intervals such that at I equals 0, x equals 0. At I equals 1, x equals 0.25. At I equals 2, x equals 0.5. At I equals 3, x equals 0.75. At I equals 4, x equals 1. We refer I as nodes. To understand better, you can refer to the number line provided in the photo. Next, we refer to the finite divided difference that was presented. Using the centered finite divided difference formulas, we can represent the second derivative, or y double prime, equals y sub I plus 1 minus 2y sub I plus y sub I minus 1 all over h squared. And substituting this equation to the original equation, we get y sub I plus 1 minus 2y sub I plus y sub I minus 1 all over h squared is equal to 4 multiplied to quantity y sub I minus x sub I. Next, we simplify this equation. By multiplying h squared to both sides of the equation, we get y sub I plus 1 minus 2y sub I plus y sub I minus 1 is equal to 4h squared y sub I minus 4h squared x sub I. We then transpose 4h squared y sub I to the other side of the equation, and we get y sub I plus 1 minus 2y sub I minus 4h squared y sub I plus y sub I minus 1 is equal to negative 4h squared x sub I. Next, we extract the common terms, and we will get y sub I plus 1 minus 2y sub I multiplied to quantity 1 plus 2h squared plus y sub I minus 1 is equal to negative 4h squared x sub I. And since we were already given that h is equal to 1/4, we substitute this value to this equation, and we get y sub I plus 1 minus 2y sub I multiplied to quantity 1 plus 2 times 1/4 squared plus y sub I minus 1 is equal to negative 4 times 1/4 squared x sub I. And finally, we came up to this equation y sub I plus 1 minus 2y sub I times 9 over 8 plus y sub I minus 1 is equal to negative 1/4 x sub I. Let us now evaluate that equations with the different values of I. We will start at I equals 0. Recall that at I equals 0, x is also equal to 0. And referring to the problem, we were given that y of 0 is equal to 0. Therefore, we can simply say that at I equals 0, y sub 0 is equal to 0. Next is I equals 1. We substitute this value of I into the last equation that we obtained, and we will get y sub 2 minus 2.25 y sub 1 plus y sub 0 is equal to negative 1/4 times 0.25. Simplifying this, we get y sub 2 minus 2.25 y sub 1 plus y sub 0 equals negative 0.0625. Simplifying this further, we get y sub 0 minus 2.25 y sub 1 plus y sub 2 is equal to negative 0.0625. Next, at I equals 2, and we follow the same procedure. We will get y sub 3 minus 2.25 y sub 2 plus y sub 1 is equal to negative 1/4 times 0.5. Simplifying this, we will get y sub 1 minus 2.25 y sub 2 plus y sub 3 is equal to negative 0.125. Next, at I equals 3. Following the same procedure, we will get y sub 4 minus 2.25y sub 3 plus y sub 2 is equal to negative 1/4 times 0.75. And lastly, we will get y sub 2 minus 2.25 y sub 3 plus y sub 4 is equal to negative 0.1875. Lastly, we will go for I equals 4. Recall that at I equals 4, x is equal to 1. Referring to the problem, we were given that at I of or y of 1 is equal to 2. Therefore, we can simply say that at I equals 4, y sub 4 is equal to 2. We got the following equations. Equation 1, y sub 0 equals 0. Equation 2, y sub 0 minus 2.25 y sub 1 plus y sub 2 is equal to negative 0.0625. Equation 3, y sub 1 minus 2.25 y sub 2 plus y sub 3 is equal to negative 0.125. Equation 4, y sub 2 minus 2.25 y sub 3 plus y sub 4 is equal to negative 0.185. And our equation 5 is y sub 4 is equal to 2. Notice that we have already obtained the values of y sub 0 and y sub 4, which is equal to 0 and 2 respectively. The next step is to solve for the unknown values. Using the Gauss elimination, we will get this matrix. And solving it further, we will obtain the unknown values of y at different values of I, which is at y sub 1, it is equal to 0.3951. Y sub 2 equals 0.8265, and y sub 3 is equal to 1.3396. Also, notice that those set of equations that we have obtained earlier were linear equations, which are easier to solve. Meaning you can solve this without using matrices. You can simply solve this using systems of linear equations or by using your scientific calculators. And the answer will remain the same. Finally, we will solve for the solution at x is equal to 0.5, which was asked in the problem. Recall that at x equals 0.5, I is equal to 2. This would mean that the value we were looking for is on what value is y at I is equal to 2 or y sub 2. And y sub 2 was already answered earlier, which is equal to 0.8265. And this will be our final answer. Y of 0.5 is equal to 0.8265. And that ends our presentation, which was about solutions to ordinary differential equations using boundary value method. Thank you, and I hope you have learned something. Merry Christmas.